Hello. So here we will be understanding about structure analysis 1, in which we are taking chapter name called strain energy, in which there are various kinds of definition. Let's understand that first. So first of all, it is strain energy. So what is strain energy? When a body is subjected to a load, let's say it can be a gradual load also, a sudden load also, or it can be an impact load also. So the body will deforms in means deflection, and work is done upon it, means load has been applied upon it, so energy is stored upon it. Let's say if elastic limit is not exceeded, this work stored in the body is called strain energy. Now let's understand through a figure. Let's here I have made one column in which it is length L, load P is been applied, so there will be deformation del L. So after applying a load there will be some deformation in the particular body, so this deformation against this load P is called as my strain energy. Let's understand by another way. If I am taking a spring over here in which I am applying a load P, so by applying load P, my body is trying to deform. If this load applied within the elastic limit, then the energy will be stored in this particular material, so this has been known as strain energy. Now it is also said that it is an internal energy stored in a material which is loaded within elastic limit. Now hence the work done stored energy is nothing but my strain energy. Now let's understand the definition number 2, which is known as resilience. Now what is resilience? Resilience is total strain energy stored in the body. Mark the word total. Means if a load W is being applied, so the amount of strain energy stored in this particular material is known as my resilience. So it is denoted by U. U means strain energy equals to sigma square by twice E multiplied by V, in which sigma is nothing but stress, E is elasticity of that particular material, V is volume. Fine. So let's understand another definition called proof resilience. Proof resilience says maximum. Proof resilience is a kind of resilience only, but a maximum strain energy. Means let's say if load W is applied, continuously going applied, so if I have stretch in within its elastic limit, so the maximum amount of energy has been stored, means maximum amount of strain energy has been stored in this particular body. So this maximum strain energy which can be stored in a body at elastic limit is called my proof resilience. It is given by UP, means proof resilience equals to sigma E the whole square. What is sigma E? This is within stress within elastic limit the whole square by twice E multiplied by V. Now another definition is modulus of resilience. It is a part of proof resilience only, but it says maximum strain energy stored in a body per unit volume. Means let's say if load P is applied, maximum load is applied, but particular unit volume the amount of energy has been saved is known as modulus of resilience. So modulus of resilience means it is also said as proof resilience per volume, means UM equals to sigma E square by twice E multiplied by V per volume. This V comes from per unit volume. The same definition has been used, but for per unit volume I have applied the divide by V, so V cancel out. My proof resilience, modulus of resilience UM will be sigma E the whole square by twice E. So these are the important most 4 definition. Now let's understand another theory. Now this theory is about strain energy due to gradual loading. Now this term gradual means load is applying simultaneously, means load applied gradually. It increases from 0 to point P maximum, 0 to point P the maximum. Let's say in a particular beam there is a load in which 0 kilonewton, then applied 10 kilonewton, then applied 20 kilonewton, and then goes up to 50 kilonewton. Means directly 50 kilonewton has not been applied, but it is increased gradually. So let's understand through a figure. If there is a bridge on which the vehicle is moving, means a kind of, let's say it can be a vehicle of truck or a kind of train. It is moving. So as one wagon, two wagon, three wagon will enter to the beam, the load will applied in this beam, particular beam, gradually from 0 to its maximum P limit. So this has been depicted that load is applied from 0 to P. Now let's understand through a graph. So now strain energy due to gradual loading, in which I have made a graph of called, one side it is load P and one side it is deformation del L. As load increases, the deformation is also increases. As load increases from 0 to maximum, the deformation will increase 0 to maximum. The same, if load has been applied, so there will be some resistance of the material, right? So if load is applied, there will be some resistance. So as deformation increase, the resistance will also increase from 0 to its maximum limit. Now this diagram has been said as load deformation diagram. This diagram is known as resistance deformation diagram. Now for strain energy due to gradual loading, for strain energy we have to compare this both diagram. Let's say how. So I am taking the area of this particular diagram. So it is a triangular. So triangular area is 1/2 base into height. So let's say area of load deformation diagram means figure A is 1/2 into P into del L. 1/2 into P is my height and del L is my base. So this is my area called equation number 1, 1/2 P into del L. Now let's consider the work stored. Now work stored means resistance deformation diagram, area of resistance deformation diagram. In this, so work stored equals to, it is also a triangular, so the area of triangle is nothing but 1/2 base into height. So 1/2 into base is del L and height is my say R. So this is 1/2 base into height equals to 1/2 into R into del L. Now let's understand this term R, resistance. Now what is resistance? Resistance will depend on, now let's see, if this is a material, if I applied a load, so the load is having some resistance. So this resistance is depend on stress into area, the amount of stress acting in this particular area. So resistance will depend on stress into area. So by replacing stress into area, so I will getting the equation number 2, 1/2 area into stress into del L. So for gradual loading we have to compare this equation number 1 and equation number 2 for stability sake. So how much amount of work done? It is 1/2 P into del L and work stored is 1/2 A into sigma into del L. So let's compare both. So strain energy is nothing but work done equals to work stored. So comparing both equation by cancelling out del L, I am getting, and 1/2 I am getting sigma equals to P by A. Stress is equal to load upon area. Its unit is nothing but Newton per mm square. So this is stress due to gradual loading. Understood? So now let's understand this strain energy term called strain energy. Now what is strain energy? The strain energy is work stored. Now what is work stored equals to strain energy? So work stored can be taken from here. So work stored is nothing but 1/2 into R into del L. Now I am using this equation over here for getting strain energy U. Let's say R, as we know that R is nothing but stress into area. So by replacing R by stress into area, so I get 1/2 into sigma into A into del L. Now let's say what is del L? Elongation based on strain. So strain is nothing but elongation upon its length. So what will we getting? Del L equals to strain into its length. So 1/2 sigma into A, and at the place of del L I will be keeping strain into its length. So I will be getting this equation. Now again, what is strain? So now let's replace it by elastic limit equals to stress upon strain. So strain is nothing but stress upon elastic limit. So by replacing that, I will be getting 1 half into sigma into A into stress upon E into length L. Now let's say sigma into sigma is sigma square by twice E multiplied by A into L. Now A into L is nothing but my volume. So ultimately strain energy is given by sigma square by twice E multiplied by V. This is also known as strain energy and also known as resilience. Sorry. Now I have kept here two theories side by side. This is, as we have studied earlier, that is, this is due to gradual load. Now this is strain energy due to sudden loading. What is meaning of sudden? Let's recall that in gradual load we are applying load 0, 10, 20 and increasing up to 50. But in sudden load there will be a direct load of 50 kilonewton directly. Let's say this spring, the load P has been applied directly the 50 kilonewton load has been applied. So here the graph will be not 0 to maximum, it will be directly the maximum value. So it is a kind of square or rectangular. Now on the opposite side, it is a low resistance deformation diagram. Here I have applied load directly, but in resistance the material has its particular resistance. It can't give the maximum directly. It will increase from 0 to its maximum limit. So the resistance deformation diagram will be same as 0 to P. Now and the deformation load deformation diagram is particularly square. Now what we have done earlier, we have to do here, that for comparing work done and work stored. So now work done is my rectangular area. So what is the area of rectangular? So it is base into height. So my height is P and my base is del L. So this will be giving me equation number 1. Now work stored. Similarly, it is a triangular. So the area of resistance is 1 half into del L into R. And we have known earlier that R is nothing but sigma into A. So replacing it, I will be getting 1 half into sigma into A into del L. This is my equation number 2. Now comparing this, work done equals to work stored, I will be getting sigma equals to twice P by A. Its units is Newton per mm square. So what it is, that gradual loading and this is sudden loading. So sudden loading is twice of gradual loading.